Okay, sound check. Video check. Looks like I'm online. Not. Hi, everybody. So looks like we're online. Yes. So thank you for joining our AI testing talks. And today is our third lecture on anomaly detection. And let me share my slides. Right, you should be able to see my slides now. Good. So, welcome to our mini course on anomaly detection for AI testing. And the lecture 3 is on machine learning approach. And my name is Rostislav Yavorsky. I am head of research at Exactpro. And before we proceed, let me just remind you maybe some basic terms of our topic. So we are speaking about outliers and anomalies. And outlier is a data point that differs significantly from other observations. And anomalies are patterns in data that do not conform to a well-defined notion of normal behavior. And we see that these definitions are not really formal. So what's really significant or what's well-defined. So that's not easy to work with this, although it's a very important area topic. And that was exactly the topic of my lecture. And I presented you several quite important applications like fraud detection, health monitoring, medical diagnosis, etc. And you can see the recording here on YouTube. Here is the link. Another issue is there are numerous challenges in anomaly detection. And the first of them is it's really difficult to define the normal behavior. And this picture on the right is a good illustration. You see some figures have some maybe one color, different colors, this kind of form and other kind of form. And so this is just random, and random doesn't mean that it's not normal. And it highly depends on your application area, on your domain. So this is the one challenge. Another challenge is that, yes, like I said, definition is domain specific. And another good example is about weather. So to have a snow during summertime is definitely an anomaly, and to have some kind of snow during the winter is definitely not anomaly. So anomalies evolve over time, and right. So there are different approaches how to define what's normal. Like to see that okay, probably this object has some average characteristics, so it's similar to many of the other objects, or it occurs quite frequently, it may be predictable. So all these approaches are used in different methods and algorithms. And that was exactly the lecture number 2, which was on statistical methods. And you can find it on YouTube. And we covered several topics like graphical methods and quartile approach, namely the QK fences, and also quite known seasonal and trend decomposition, which is quite good for time series analysis. And also we had another topic on statistical hypothesis test, p-value, and t-statistics. So that was shortly the overview of previous 2 lectures. And today we'll speak about machine learning. So I like really this picture because it provides us kind of a map of machine learning methods and algorithms. And you can see that actually there are 3 different directions, approaches, areas. So once you decided to apply machine learning to your task, you have 3 options. Either you work with unsupervised learning, which are actually about clustering and dimensionality reduction. The second option is you work with supervised learning, which is more about classification and regression. And the first currently under development area is about reinforcement learning. So it's quite promising, but still rather new direction. So if you try to see which of these topics are more relevant to anomaly detection, you will find several. And let's see some of them, like customer segmentation. Although it sounds maybe slightly different, you can in some sense think about your data points like customers. So you have like one data point, another data point, and at some point, finally you get some outlier, so you can think about like, okay, you need to do something with this customer, so it's different. So in some sense, the methods used for customer segmentation could be also applied from anomaly detection. Another quite promising area here is structure discovery. Because like I said, the main idea in anomaly detection is first to define what's normal, what's kind of expected. Since so if you can discover some structure, understand some kind of the logic, the inner logic of your system, then it will be very helpful for you to describe anomalies. So everything which doesn't fit into this structure is definitely an outlier or anomaly. There are also some supervised learning approaches which are kind of related to prediction or classification, because actually what we need to do in outlier detection to classify your data into normal data and not normal data. So definitely it's classification task. And also you can use predictions, because again, if something is predicted, then probably it's more or less normal. But if you have kind of unpredicted behavior, then surely it's kind of candidate or signal for anomaly or outlier. So let's start with unsupervised learning, and that will be actually the main part of today's lecture. So right, so the objective of this approach is to detect some rare objects or events without any prior knowledge. So you know nothing about your system, so you don't have any kind of teacher or whatever or structure. So you just have your data set. So the goal is to figure out where are outliers and anomalies. So there are two quite simple, at least they look simple, steps. The first one is to model the normal data distribution, and second, to define how far some data points are from this normal distribution. So, and actually the first step is probably the most difficult. So, because once you have definition of normal, then it will be more or less easy to figure out what's not normal. And in this step, you have two different sub-steps or options in unsupervised learning. The first one is called clustering, which is actually grouping. So you need to group your data in some kind of normal groups, and then you'll see what's not normal. And the other approach is called dimensionality reduction, and it's actually dimension is the number of parameters. So quite usually in applications you have huge number of different characteristics and parameters which describe your data. And to reduce them is actually to figure out the internal structure, internal logic of your system, and that will definitely will help in anomaly detection and outlier detection too. So let's start with clustering. And here is the definition. So clustering is the task of dividing the population or your data points into a number of groups. So what kind of groups? Such that data points in the same group are more similar to other data points in the same group than those in other groups. So again, this is a kind of more or less formal, but again, we depend on the notion of similar. And but this could be formalized by the notion of distance in your space. So, okay, let's see. So there are three main approaches to clustering, three types of clustering algorithm. The first type is called connectivity, and it's based on distance connectivity. So, so you just try to figure out that, for example, some data points, some elements of your data set are quite close to each other. Definitely, if they are close and with small distance, you group them into one cluster, and then you iteratively go one by one, trying to find kind of nearest neighbor and from these groups, and then you combine small groups into bigger groups, and finally you get kind of hierarchy of different clusters. This is the connectivity approach. The second approach is based on the idea of centroid. This is the picture on the right. This kind of visualization is called Voronoi diagrams. The idea is that in first you select these black points, you see, and you kind of decide that they are kind of a single data point, which is in some sense most typical. And then you decide that the cluster is exactly, so the number of points which are closest to this one, which are closest to this one, and then put another one. So for example, you take this point somewhere here, then you compute distance to this centroid, to the other one. Okay, no need to compute this because they are quite far. So, and then you check if this one is closer, then this point will go into this group. If the other one is closer, the distance is smaller, then this data point will go into that group. And that's actually the idea of centroid models. So you need to find these kind of typical representatives, and then they will kind of be the base for defining your groups. And the third approach is is based on density models, and they defined. So you see this picture on the right. So you compute the density. So if you see some areas which are kind of densely populated, like dark green here or dark blue here, then definitely this dense area is some meaningful. It's reasonably just to decide that this is a cluster, and then you have another one, and then you have a kind of light blue area here, which is on the border, and some light green area there. So, and finally, you'll get some data points which do not belong to any dense area, and they will be probably candidates for outliers. And similarly, in this case, once you decided, and usually it's not just immediately, so you maybe take some candidates for centroids, and then you don't like these candidates, you recompute, you suggest another one. So finally, you decided that these black circles are centroids. Then once you get some point here, you compute distance to all of them. And if it's quite far from every centroid, that's probably a reason to decide that this is anomaly or outlier. So let's see, okay, funny and simple yet important example of agglomerative bottom-up algorithm. So this is our data set. Right, I try to be simple, but in real life, you never have data set of 8 elements. So much typical is to have 8,000 or maybe 8 million. But okay, for this lecture, we have data set of just 8 elements. You have rabbit, chick, hen, duckling, dog, goose, rooster, and a cat. So, as I mentioned, agglomerative approach is based on the idea to find kind of similar, like, okay, let's start from chick, for example. Okay, it's small, it's yellow, it has 2 legs with quite different, okay, So it looks a little quite different than the other part of bodies. So let's see if you have something like this, and definitely darkling should be in the same cluster as the darkling should be in the same cluster as the cheek, right? Because the shape is similar, legs are similar, color is similar. So cheek and darkling should be in one cluster. Okay, let's see the rabbit. So okay, it has looks like 4 legs. It's okay, fuzzy and color, and okay, the ears are quite big. Okay, let's see something similar, and you realize that especially in this data set, the cat probably is should be in the same cluster, right? Because they are quite similar. And then we go on, so we can see the hen. Okay, hen probably and goose here look quite similar, although the colors are not the same, but the shape of the legs, okay, no ears, and okay, just 2 legs. So you probably put hen and goose into one cluster, and finally you'll get picture like this. So you have definitely cat and rabbit in one cluster, and maybe dog is in the same cluster, or we may decide that dog is close but separate cluster. It depends on the threshold. You will at some point will have to decide either you need to have many small clusters or maybe fewer big clusters. But anyway, dog is definitely quite similar to the cat and the rabbit. And similarly here, you have hen, goose, and maybe rooster. Either you put it in the same cluster as hen and goose, or it's different. So what I am showing now, I do it manually, but surely you can easily formalize it, and there are a lot of different implementations on the web. So you just apply agglomerative bottom-up algorithm, and you end up with this number of clusters, and then you get some new data. Okay, intuitively, you feel like fish is not typical here, so it should be probably anomaly. But what we discussed previously during previous lecture, you will prefer to have it done formally, not with no human involvement. So you would like to have some formal algorithm which checks some conditions and then makes clear decisions for you that, okay, this is anomaly and this is not. So let's see this example. So once we use clustering approach to anomaly detection, first we defined normal behavior in terms of several clusters. Like here, we say that normal data means that it's either something like cat, dog, or rabbit, or it sounds like duckling, chick, or it should be something like hen, goose, or rooster. Everything else is considered as not normal, as anomaly, as outlier. And this is exactly the example. So we see that fish doesn't look like dog or cat. It neither look like chick or duckling, and hardly similar to hen or goose or rooster. So this is anomaly, surely. That's actually the idea of clustering approach. So you first divide your data set into several clusters. Then you check how far each new data point from this each of the clusters. And if it fits into a cluster, then definitely it's okay. It's kind of normal behavior. If it doesn't, then it's surely a candidate for anomaly. Maybe one small addition. So sometimes anomaly may look different. For example, you are analyzing your data. We have this example in our application. So you have this data, and you usually have like 10 clusters and like 5 small clusters and 5 big clusters. And next day you have again these 10 clusters, but one of the smallest clusters started to grow. This could be another indication for anomaly. But anyway, clustering approach is very powerful. It's okay, everyone likes it because it doesn't require any human involvement. So you don't need any teacher, no. Okay, surely you need to spend some time on configuring your algorithm, but otherwise it works automatically. Okay, let's see the other approach of anomaly detection, which is called dimensionality reduction. And since not everyone is a professional mathematician, I really suggest to start with some basic definitions. So actually, dimension is just a fancy word for just number of parameters. So the dimension of data set corresponds to the number of attributes that exist in data set. So for example, you have this table on the right, and this is most typical representation of your data set. So you have each row represents your kind of observation, your objects, and then the columns are actually the parameters of your observations. And the dimension of the data set is actually the number of parameters, period. So usually, again, it's kind of magic number, but if you have maybe 10 parameters or maybe even 20, that's considered like a small dimension because you still can work with it. You can somehow visualize it and try to look at each parameter separately. But if the number of attributes is more than 100, it's definitely a high dimension. And okay, so what the idea of dimensional reduction is the transformation of data from a high dimensional space into a low dimensional space, so that the low dimensional space representation retains some meaningful properties of the original data. So you see this example on the right. So actually the idea of dimension came from geometry initially, and in our kind of standard Euclidean geometry, we have 3 coordinates, which means that the dimension is 3. But for example, you have kind of some plane figure in 3 dimensions, then formally it is 3-dimensional. But if you just try, for example, you have a triangle, then you can transform this triangle into a different coordinate system so that it becomes 2-dimensional. That's basically the idea of a dimension reduction. So let's see some examples from real life. I like this example. It's pretty much related to what we do here. It's about software defect prediction. So it's created by NASA, and so you see some description of this data. So it's just 10,000 modules, and each module consists of some code, and then 22 different attributes are measured for each of the modules. So like I said, 22 is quite a small number of parameters. You can, for example, build a graph for each parameter, maybe write some report, print it on in maybe some visual form on a piece of paper, then put those 22 pieces of paper on your table. Okay, you probably need big table, but this is still feasible. And then maybe combine, try to figure out what's going on. So, and this data set is available for free online on kaggle.com. But the other example is probably more typical for our business. It's an example for operational data from enterprise application. And this data set has 27,000 files. This is not typo. So just the number of different files is huge. And file is not a data point. It's a collection. It's another data set. So the total number of parameters is more than 4 million. And definitely you cannot build a graph for each of, okay, surely you can maybe run a script to build a graph, or maybe some automated analysis for each of the parameters, but finally you'll get 4 million pages of such analytics. Okay, to read 4 million pages of analytics, it's not something you probably want. So this is definitely, but the task is very practical. You need to detect some runtime anomalies. Okay, you are free to apply any method you like. Machine learning is okay, clustering okay, dimension reduction surely yes, but surely you will start probably with the idea of reduction of dimension, because to work with 4.5 million columns is it's difficult. Okay, you would prefer maybe to have maybe 10, 20 kind of aggregated parameters. So you see the idea of dimension reduction is very practical. So let's see the scheme. So there are two different approaches how to reduce the number of dimensions. One is just drop most of the attributes, because indeed, if you try to collect data, if you maybe data engineer, you try to measure everything, right? The more information, the better. But at this point, maybe if you turn to especially to anomaly detection, it may turn out that most of the parameters are not important. So you need some algorithm, some approach to figure out which features, which parameters, which attributes are not important. And then there are three: backward elimination, forward selection, random forests, etc. So the idea is simple. So you just figure out maybe 20 the most important features, and you just forget about the rest. So the only tricky part is to figure out which particular features to keep. Okay, the other more kind of powerful, definitely, but more difficult approach is to find combinations of new features. So, for example, you can take like usually linear combinations or maybe 10 features with some weights, and then you will get one feature which will take into account all the parameters. And there are two sub approaches here. The first one, more simple but still very powerful, is linear methods, and the other one is about non-linear approaches. So and today we'll speak a little bit about linear approach. So you have PCA stands for principal component analysis and factor analysis, and there are the other one. You can surely find a lot of information on the web. So today I will cover those two, PCA and factor analysis. So let's start with principal component analysis. The idea is quite simple, that new variables are linear combinations of the initial variables. So these combinations are done in such a way that the new variables are uncorrelated. That's the basic idea of this method. So if two or more variables are correlated, then probably they describe the same kind of internal feature of your system. Then you just take a combination of those. But the idea is to end up with maybe small number uncorrelated parameters. And yes, so here just a list of prerequisites. So in order to really understand what's going on inside this method, you probably need some mathematics, some mathematical background. And here is a short list. So you need some knowledge from linear algebra. So it's better understand what's matrix multiplication, transposition, inverse, decomposition. Very important notion is eigenvectors and eigenvalues. And you'll definitely need some knowledge from statistics related to standardization, covariance, independence of variables, and some basic understanding of linear regression and feature selection. So, okay, that's not really each of the terms is more or less simple, and maybe you may spend 1 hour just reading some literature to understand the idea, but you need all those to understand how principal component analysis works. But in case you are lucky and you you already know all of those, so let's go ahead. Okay, this slide probably is the most difficult part of my lectures, so it's okay if you don't understand. But if you do, so here are the 5 steps of principal component analysis. So first, you start with normalizing the initial variables. So you may have that one variable measures some like millimeters, and the other one is about kilograms, and the other one is kind of some time values. So first step is to normalize that each variable range from, it's like from -1 to 1, something like that, or from 0 to 1. Then you compute the covariance matrix, namely the correlations between all possible pairs of variables. For example, like you have 1,000 different parameters, then this matrix will consist of 1,000, 1 million different pairs. So it will be symmetric, definitely, but 1 million is still a big number. Then you compute eigenvectors. Don't ask me what this. It's quite tricky, but quite interesting idea. And the rank them in the descending order. And then the idea is similar to the first approach. You just decide which of those vectors to keep, and you just drop the rest. So you see, this is a more kind of a typical picture from principal component analysis. So here you have numbers of vectors, which we call them principal components, and here you have percentage of explained variances. So you see that this component is kind of responsible for 40% of different variances. So definitely we should keep this vector. Then the second one is also quite influential, etc., etc. So on this picture, if you, for example, stop here, you will reduce your dimension to very small. You will have just 6 vectors, which means that your dimension will be just 6, which is very small. But still, your system will be quite well explained, well described by those 6 vectors. And then you just rearrange the data from the original axis to the ones represented by principal components. Okay, alive? Clear? So again, so this is quite interesting method. So, but before you try to understand what's going under the hood, you should probably learn some algebra, statistics, and basics of machine learning. But anyway, this is quite quite useful and very powerful method. And the other one is called factor analysis, and actually it's kind of advanced version of principal component analysis. And the idea is described on the picture on the right. So you assume that your data, so here's you kind of, for example, you have, okay, again, very small. In real life, it may be not 8 by 8,000 different parameters, but assume we have like 8 parameters which actually describe our system. And we assume that actually the number of real factors which influence our behavior are just 2. So we assume that there is some kind of factor A and factor B, which are responsible for the behavior of the system. And then this graph shows the influence. So for example, factor A influence vectors variables 1, 2, 3, 4, 5. And this factor is responsible for those variables. And you see some variables could be affected by the both factors, etc. So the idea that you assume there are some unobserved variables, you call them factors, and then you find those variables and you try to reduce to use to reduce the number of variables into just fewer number of these factors, just to describe the system. So, and again, why do we need all those really difficult techniques for anomaly detection? Because this is a standard approach to define what is normal behavior, what is a normal structure of your data. So once you have this definition, and let me remind that we are working with unsupervised, so this structure is detected autonomously. So the algorithm does it without any intervention of human. So you have this definition of normal. Once you have it, you can decide that, okay, this is outlier, this is anomaly. Okay, and right, that's already said. So, right, there are two different types of factor analysis, and the first one, if you don't have any idea about your data, and sometimes you may have some ideas about what factors look like, then you apply different modification of this analysis. But again, I suggest you maybe to read some specific literature. This is very powerful technique, but it really requires some mathematical background. So before conclusion, let's say a couple of words about supervised learning. And you see this picture on the right. It's actually the standard scheme of supervised learning. Doesn't matter, you apply to anomaly detection, classification, prediction, whatever. So you have some labeled data, but before you have predefined set of labels. This is the principal difference from clustering. If you apply clustering, you don't know what kind of clusters you expect. You know nothing about your systems. But here you already know a priori before you start, you know the set of predefined labels. And in some sense, it's exactly what we have in anomaly detection. We have just two labels, like normal, not normal. Then what's problem of applying this approach to anomaly detection is to have labeled data. So you can easily build a huge data set which is labeled like normal. But the problem is it's easily difficult to build a good labeled data set of not normal behavior. So that's why this approach is rarely used due to non-availability of labeled data for the known anomalies. But sometimes, for example, in which domain you may already have some maybe historical data about different faults, about maybe frauds, etc. And you can use this data in your supervised anomaly algorithm. Then definitely you can apply all these methods. Okay, so to conclude, surely there are a lot of different already implemented libraries and algorithms, and I just maybe recommend one of them. This is Anomaly. It's a library for benchmarking, developing, and deploying deep learning anomaly detection algorithm. And here is the link. And surely there are different libraries and tools. And also the book. I read some chapters while preparing this lecture. I really like it, so I decided to recommend it to you. This is just exactly a book on unsupervised learning using Python. And again, you can see the link here. So that's actually all I have for today. Thank you. And surely you can write some questions in the comments to this video, and we'll continue our AI testing talks, and I plan to answer all of them, and maybe for some interesting questions we'll have maybe even separate lecture, some examples and discussion. So thank you very much. That's it. Bye.